Hello and welcome back. In the previous video, we discussed the formulas for calculating the forces that are exerted on charged particles. Now, one important thing to understand about these forces is that they are conservative, and this means that we can associate a potential energy with the work that is done by these forces. Now recall, in the previous videos, there were two different formulas that we came up with for calculating the forces that are exerted on a charged particle. The first of these was Coulomb's law, which describes the forces that are exerted between 2 point charges. And that's given by this formula here. The second formula describes the force in terms of the electric field, and it's given by this formula here. And what I would like to do in this video is I would like to describe how we calculate the potential energy that is associated with these two formulas. Now, before we derive the formulas for the potential energies that are associated with these two force formulas, I first want to review the relationship between the work that is done by a conservative force and the change in its corresponding potential energy. Recall that the difference in the potential energy between 2 points is equal to minus the work that is done in moving from that initial point to the final point. Furthermore, recall that work describes the tendency for a force to either increase or decrease the kinetic energy of an object. And remember that it is the component of a force that is parallel to the displacement that tends to speed up or slow down an object. And this is why work is equal to the component of the force that is parallel to the displacement times the displacement. Now, the reason this negative sign is here is because according to the work-energy theorem, work is equal to the change in the kinetic energy. And remember that when the kinetic energy of an object increases, the potential energy has to decrease. So that's why this negative sign is here. So now that we've reviewed how to calculate the potential energy, let's calculate the potential energy that is associated with the charged particle in an electric field. So remember, the difference in the potential energy between 2 points is equal to minus the work that is done in moving from the initial point to the final point. And remember that the work is equal to the component of the force that is parallel to the displacement times the displacement. And if we have a charged particle that is inside an electric field, the electrostatic force that is exerted on the particle is equal to Q times the electric field. And since we're only concerned about the component of the force that is parallel to the displacement, we only want to include the component of the electric field that's parallel to the object's displacement. And so this formula that I have right here describes the difference in the potential energy between 2 points. So let's go ahead and look at an example. This example says, an uncharged mass is thrown vertically upwards in an area that contains an electric field, and this electric field is also going to point in the vertical direction. When the object is thrown upwards with an initial speed of 25 meters per second, the object obtains a maximum height h. When the mass is given a charge plus q and thrown upwards with an initial speed of 30 meters per second, the object obtains the same maximum height. So the question asks, if the object was given a charge minus q, how fast would you need to throw the object vertically upwards so that it would also attain the same maximum height? So the first thing I want to point out about this is because the positive charge needs to be given a larger initial velocity, we can see that the electrostatic force is pushing down on the positive charge. So this means the electric fields are pushing down on the objects. Also, for the negative charge, this means that the electrostatic force is going to point in the opposite direction. So the electrostatic force is going to be pulling upwards on the negative charge. So this means that when we throw the negative charge into the air, we won't have to give it as much of an initial velocity for that object to reach the same final height. So this picture right here kind of just describes this problem. So if we have a neutral particle, we need to throw it up with a speed of 25 meters per second to reach this final height. And if we're given a positively charged particle, the particle has to be given an initial speed of 30 meters per second in order to reach the same final height. So let me go ahead and open up a blank screen. So I've written down some of the information that was given to us in this problem. And I'm using a notation that I think is very useful for working through this problem. I use a subscript 0 to describe the neutral particle a subscript with a plus sign to describe the positively charged particle, and a negative subscript to describe the negatively charged particle. And one of the tricks to solving this problem is realizing that the potential energies of these three particles are all going to be related. So for example, because all of the objects reach the same final height, the final gravitational potential energy of the neutral particle is going to be equal to the final gravitational potential energy of the positively charged particle, and that's going to be equal to the final gravitational potential energy of the negatively charged particle. And because all of these potential energies are the same, I'm just going to refer to this as the gravitational potential energy. Additionally, remember that the potential energy that is associated with the electrostatic force is given by this formula here. It's Q times the component of the electric field that's parallel to the displacement times the displacement. And in this case, the displacement is just the height that the object reaches. So this is going to be the same for all of the particles. So what this means is that because S is the same for all the particles, and because the electric field depends on the charge of the particle, the final electrostatic potential energy of the positively charged particle is going to equal minus the final electrostatic potential energy of the negatively charged particle. So this is how these two potential energies are going to be related. Now, because the electrostatic potential energy depends on the charge, and because the neutral particle has no charge, the electrostatic potential energy of the neutral particle is always just 0 joules. So if we apply conservation of energy to the neutral particle, this is very simple. So you're throwing the object up into the air, and the object's going to reach some final height. So we'd say that the initial kinetic energy of the neutral particle is going to be equal to the gravitational potential energy. So this is the only formula we have for the neutral particle. For the positively charged particle, it's a little bit more complicated. The initial kinetic energy of the positively charged particle is going to be converted into gravitational potential energy and electrostatic potential energy. Finally, if we look at the negatively charged particle, we have a very similar formula. So the initial kinetic energy of the negatively charged particle is going to be equal to the gravitational potential energy plus the electrostatic potential energy of the negatively charged particle. And so the idea is that I can actually use these three formulas, and what I'm going to do is I'm going to combine these in a way to get a single formula that only depends on the kinetic energies of these three particles. That way I can relate the velocities of the particles, and I can solve for the velocity of the negatively charged particle. So the first thing I'm going to do is I'm going to plug the kinetic energy formula into here to get rid of the gravitational potential energy. So the initial kinetic energy of the negatively charged particle is equal to the potential energy due to gravity plus the electrostatic potential energy. But the gravitational potential energy is just equal to the initial kinetic energy of the neutral particle. Additionally, I can rewrite the electrostatic potential energy of the negatively charged particle as being equal to minus the potential energy of the positively charged particle. And then what I can do is I can use this formula here and plug it into here. So the potential energy of the positively charged particle is equal to the kinetic energy of the positively charged particle minus the gravitational potential energy. So this is equal to the kinetic energy of the neutral particle minus, and this is equal to the kinetic energy of the positively charged particle minus the gravitational potential energy. So this is going to be equal to 2 times the kinetic energy of the neutral charged particle, because remember this is the kinetic energy of the neutrally charged particle, and I have minus and negative, so that gives me 2 times the kinetic energy of the neutral particle minus the kinetic energy of the positively charged particle. So we have this formula right here. So because it's the same particle for all of these, the masses are going to cancel. So I have 1/2 m times the initial velocity of the negatively charged particle squared is equal to 2 times 1/2 times the mass of the neutral charged particle squared minus 1/2 m times the initial velocity of the positively charged particle squared. So the 1/2 m's cancel everywhere, and we see that the initial velocity of the negatively charged particle squared is equal to 2 times the initial velocity of the neutral particle squared minus the initial velocity of the positively charged particle squared. So if I solve for the initial velocity of the negatively charged particle, I'll see that this is going to be equal to 18.7 meters per second. So this is a very simple way to solve the problem where we don't actually ever solve for the height that the object reaches. We just use these relationships between the potential energies of the positively charged particle and negatively charged particle. So let's go ahead and look at the other formula we have for the electrostatic force. Recall that Coulomb's law says that the force that is exerted between two charged particles is equal to k q1 q2 divided by the distance between the charges squared. Now there are two things that I want to point out about this formula. The first is that notice that the magnitude of the force decreases as the distance between the charges increase. And what this means is that we say that when the charged particles are very, very far apart, the potential for this force to do work is very small. So we define the potential energy of the charged particles to be 0 when the charged particles are infinitely far away. The second thing I want to point out about this formula is that the magnitude of the force changes as the distance between the charged particles change. So when we calculate the work that is done in moving the charged particles, we're going to have to use integrals. So the work that is done in moving the charged particles some very, very small distance is going to equal k q1 q2 divided by the distance between the particles squared times the very small distance that I move the charged particles. Now, if I want to calculate the work that is done in moving the objects a large distance, I'm going to have to integrate this. And so I'm going to integrate this from some position r out to infinity. And the reason I'm going to take this out to infinity is because I've defined the potential energy at infinity to be 0. So if I integrate this work, I get this is going to be equal to the work at infinity minus the work at this point r, and I'm going to define the work at infinity to be 0. And this is going to equal, so k, q1, q2, these are all constants, so I can pull those out, and it's going to be an integral from r out to infinity of 1 over r squared. So if we think about this, this is r raised to the minus 2 power. And if you integrate r raised to the minus 2 power, this is equal to minus 1 divided by r. So over here, we have minus the work that is done by r is equal to k q1 q2 times minus 1 over r, and now we have to evaluate this between our endpoints. So if we evaluate this, we have k q1 q2, and at infinity this is going to equal 0, and at the other point this will equal minus 1 over r. So we have 0 minus a negative 1 over r, so that's positive 1 over r, but we still have the negative sign over here, so the work that is done is going to be equal to minus k q1 q2 divided by r. Now because the potential energy is equal to minus the work, the potential energy that is associated with two charged particles is equal to k q1 q2 divided by r. And so this is a very simple formula. It's actually really easy to remember. If you remember that work is equal to the force times distance, this is kind of a cheat way to get at it. It's not really a proper way, but if we say that the force is equal to k q1 q2 divided by the distance between the particles squared, and then if I just multiply that by the only distance we can think of, which is the distance between the charged particles, I suddenly wind up with the right formula. So this is not a correct derivation. This is not the proper way to derive this formula, but if you have a hard time remembering it, this is a very quick and easy way to remember the relationship between the force and the potential energy. So let's go ahead and look at a couple of examples. The first example says, two identical point charges are fixed to diagonally opposite corners of a square which has sides of length 0.5 meters. The charges are each 3 times 10 to the minus 6 coulombs. The problem asks us to calculate the amount of work that must be done to move the charge from its opposite corner to one of the empty corners. So I have a picture here showing what we're talking about. So the charges are initially at diagonally opposite corners, and I want to calculate the amount of work that would be done if I move this charged particle up to the empty corner over here. So the idea is that, remember that when you exert a force on an object to push the object, that force that you're pushing with is a non-conservative force. And remember that the work that is done by a non-conservative force is equal to the change in the total energy of the system. And in this case right here, the only energy that we have is the electrostatic energy. That's the energy that is associated with the Coulomb force between the charged particles. So we can say that the work that is done is equal to the change in the electrostatic potential energy. And remember that the electrostatic potential energy, we just found that that's K Q divided by the distance between the particles. So we're going to calculate the final minus the initial. And I can factor out KQ squared because that appears in both of these. So I have KQ squared times 1 over the final distance minus 1 over the initial distance. So the last thing I need to do, K is a constant, we know that. We were given Q. The final distance is going to be 1/2 of a meter. And the initial distance, if we think about this, this is a triangle here, right? Both of the sides are going to be 0.5 meters. So the initial distance between these charged particles is going to equal 0.5 meters squared plus 0.5 meters squared square rooted, which is equal to the 0.5 meters times the square root of 2. So that is our R initial. So if we plug that initial distance into this formula here, we plug 0.5 as our final distance into the formula here, we'll see that the work that is done when we move the charged particle from the diagonally opposite corner to the empty corner is equal to 4.7 times 10 to the minus 2 joules. So let's go ahead and look at another example. This next example says a proton is moving directly towards another proton, which is initially at rest. When the protons are very far apart, the proton has an initial speed of 3 times 10 to the 6 meters per second. The question asks us, how close will these two protons get? So the idea is that this proton over here has some initial kinetic energy, and as this proton gets closer and closer to this other charge, its kinetic energy is going to be converted into electrostatic potential energy. And at this point right here, when the particle turns around, its kinetic energy is going to go to 0, and all of its initial kinetic energy will have been converted into electrostatic potential energy. So the idea is that the initial kinetic energy of the charge is going to be converted into electrostatic potential energy. So we have 1/2 mv initial squared is going to be equal to, and this is going to be K times the charge of the particle squared, because it's a proton, that's E squared, divided by the distance between them. Actually, that should be the charge of one particle times the charge of the other particle, but they're both the same, so it's the charge squared. So here all I need to do is solve for this final distance. So I see that R final is going to be equal to, so I'm going to multiply the R final over here. Actually, let me not skip any steps. So I'm going to multiply R final over to the left side, so we'll have 1/2 mv initial squared times R final is equal to K E squared. And so I'm going to divide off the 1/2 mv naught squared. So R final is going to be equal to 2K E squared divided by mv naught squared. And this is a proton, so I can look up the mass of a proton. Remember, the charge is 1.6 times 10 to the minus 19 coulombs. We have K as a constant, so we can plug all this into a calculator, and if I do that, I see that the final distance is going to be equal to 3.06 times 10 to the minus 14 meters. So the protons will get very, very close to each other. Of course, 3 times 10 to the 6 meters per second is a very high speed. So we've seen how to calculate the potential energy between 2 charged particles, but how do we calculate the potential energy between 3 or 4 charged particles? The answer is that the total potential energy is equal to the sum of the potential energies for each pair. So what exactly do I mean by that? Well, let's go ahead and look at an example. So the total potential energy of this system is going to equal the potential energy associated with these 2 charged particles. So I might call that the potential energy associated with charge A and B, plus the potential energy associated with particles A and C, plus the potential energy associated with particle A and D. So this gives me these 2 particles, these 2 particles, and these 2 particles. Now I can talk about the potential energy between B and C, the potential energy between B and D, and then finally the potential energy between charged particles C and D. So one of the things you'll immediately notice about this is that calculating the potential energy between multiple charged particles can very quickly become a very complicated problem. So typically when you're working through your homework, you'll be dealing with 2 or at most 3 charged particles. I'll never give you 4 because, as you can see here, calculating the potential energy of 4 particles is just a bit cumbersome. So let's go ahead and look at an example where we calculate the potential energy between 3 charged particles. So I'm given a charge distribution down here, and I want to calculate the potential energy associated with this charge distribution. Now, because the potential energy between 2 charges depends on the distance between the charges, the first thing I want to do is calculate the distance between these 2 charged particles here. So this is going to equal the square root of 5 meters squared plus 12 meters squared. And if I plug that into a calculator, I see that this is going to equal 13 meters. So this is another one of those perfect triangles. So now all we need to do is we need to plug into the formula for the potential energy between 2 charged particles and add that up for each of these 3 pairs. So the total potential energy is going to equal, so this is going to be K times 3 microcoulombs times 5 microcoulombs for these 2 charged particles, divided by the distance between them, which is 5 meters, plus K times, so for these 2 particles at the bottom, this is going to be 5 microcoulombs times negative 8 microcoulombs, divided by the distance between those charged particles, which is 12 meters. And then finally we have this pair right here. So this is going to be plus K times 3 microcoulombs times, again, negative 8 microcoulombs, divided by the distance between these particles, which was 13 meters. And if we plug this into a calculator, we'll see that this is going to equal minus 1.96 times 10 to the minus 2 meters. And one thing I want to point out about these negative potential energies is that whenever you have 2 particles and they're exerting an attractive force on each other, we say that the potential energy that is associated with that force is a negative potential energy. And anytime there is a repulsive force between 2 particles, we say that the potential energy associated with that force is going to be a positive potential energy. Now obviously here, in this charge distribution, it's a little bit more complicated than that, because some of the particles are repelling each other and some of these particles are attracting each other. But the fact that this potential energy is negative tells me that the potential energy associated with these 2 particles and these 2 particles is greater than the potential energy associated with these 2 particles, or at least larger in magnitude. So at this point, I think I'd like to end this video, and in the next video I'm going to talk about something called potential, which is usually referred to as voltage.